Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 16, 2026, just 2 days ago. It introduces a new generative framework capable of producing high-quality images in a single forward pass, competing with many step diffusion models while using fewer than 5 inference steps. The paper is titled, Image Generation with a Sphere Encoder. And as we'll see later, the results are really impressive, potentially offering a much faster alternative to current state-of-the-art models. So Figure 1 immediately shows us what this looks like in practice, with a grid of generated samples. The top sections display images from CIFAR 10 and animal faces produced in a single forward pass, which highlights the sheer speed of this approach. Just below that, we see Oxford flowers generated in 2 steps. Then, the large bottom section features diverse ImageNet samples created in 4 steps, which demonstrates that the model handles complex subjects effectively without needing a long iterative process. Alright, having seen the outputs, Figure 2 breaks down the actual mechanism. The process starts with the encoder, labeled E at the top, which maps a natural image onto a high-dimensional spherical latent space, shown here as the blue sphere S. The goal is to distribute these image embeddings uniformly across the surface. Then, for generation, the model samples a random point from this sphere and passes it through the decoder D, producing a new, realistic image, like the B shown at the bottom. Well, while Figure 2 showed the ideal mapping, Figure 4 reveals the training trick that makes it work, spherifying with noise. Here, the encoder E maps the input image, like this baseball, to a specific point V on the blue spherical surface S. Crucially, before decoding, the system adds random Gaussian noise to perturb the vector and reprojects it back onto the sphere, creating those gray, shifted points shown on the curve. The decoder D is then tasked with reconstructing the original image from this noisy input. This strategy forces the decoder to understand the entire local region around an embedding, ensuring the latent space becomes a smooth, continuous manifold rather than just a set of isolated points. So while the previous figure explained the training noise, Algorithm 1 details the actual generation steps. The process begins at the top with a random noise vector, labeled E, which is directly decoded into an image for 1-step generation. But for higher fidelity, the method enters a refinement loop, shown in the bottom half. In this stage, the model iteratively re-encodes and decodes the image, applying classifier-free guidance in both latent and pixel spaces to enhance the details. Okay, having detailed the algorithm, Table 1 presents the quantitative results on CIFAR 10. The top section focuses on conditional generation without classifier-free guidance. Here, the sphere L model improves rapidly, and by step 6, it achieves a generation FID of 1.65, which outperforms the StyleGAN 2 baseline. In the bottom section for unconditional generation, the efficiency gain is even clearer. While standard diffusion models like DDPM require thousands of steps to reach an FID around 3, the sphere L model achieves a superior score of 2.34 in just 6 steps. Alright, moving from CIFAR to the much harder ImageNet dataset, Table 3 compares this approach against major baselines at 256 resolution. The table groups methods into GANs, diffusions, and the new sphere models at the bottom. Notice the steps column for diffusions. Models like ADMG or SID often need hundreds of steps, sometimes up to 1,000, to reach convergence. In contrast, the sphere XL model at the bottom requires just 4 steps. Despite this massive speedup, it achieves a generation FID of 4.02, which actually beats the ADMG baseline that uses 250 steps, highlighting the efficiency of the spherical mapping. So, while the previous comparison established the model's speed, Table 4 dissects exactly which training objectives drive that quality using an ablation study on ImageNet. The first row shows the baseline using only pixel reconstruction loss, which yields a relatively poor generation FID of roughly 25 without guidance. Adding the pixel consistency loss in the second row drops this error significantly to around 17 because it helps the decoder handle noisy inputs. Finally, the bottom row adds latent consistency loss, which refines the manifold even further, allowing the model to reach its best FID of 7.28 when using classifier-free guidance. Wrapping up, the big takeaway is that we might not need expensive diffusion loops for high-quality generation after all. By mapping images to a spherical latent space, this model delivers competitive results in a fraction of the time, paving the way for faster, real-time creative tools. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.